So we're going to look at situations where objects, where they experience momentum in 2 dimensions. So prior to this, we've only looked at situations, where an object is moving either, say, left or right, and all that happens is just in that 1 dimension, or possibly up and down. We've gotten a hint in a couple problems where there's been 2 dimensions, but for the most part, we haven't. The question is what if we have an object that's not moving in, well, it's hard to have an object not moving in 1 dimension. For example, even if the object was moving that way, I could still call that, I could tilt my head and call that my x-axis, couldn't I? But let's say you have one object moving that way and another one that's moving, say, this way. Now there's no way I can make those into 2 separate dimensions. So what we want to keep in mind is that if you have an object whose momentum vector is, say, directed that way, you are going to have to treat, because it's a vector, you're going to have to treat its x component and its y component completely separately from each other. So when we talk about conservation of momentum, where we have been saying that the momentum initially equals momentum at the end, really now we're looking at, if you have a situation where you have objects moving at other than 2 dimensions, you have the original x momentum should equal the final x momentum, and at the same time you have the original y momentum equals the final y momentum. So, well, you could reverse the original and x, doesn't matter. But you have really 2 problems inside of 1 now. Just a reminder, if you have a reference angle, the angle to the x-axis, your y component, of course, is going to be the original momentum times the sine of that angle. And your x is going to be momentum times the cosine of that angle. That's old stuff. If a problem, be on the lookout for this, if a problem gives you an angle to the y-axis, it gives you this angle, which is really the complement to the reference angle. So I'll call it phi. If it gives you that angle, then your y component is going to be found using the cosine of that angle, and the x component is going to be found using the sine of that angle. Or your other option, of course, is if you know this angle, to just subtract it from 90 to find your actual reference angle. It's up to you how you want to handle that. But just be aware that some situations they may not give you the reference angle, they may give you its complement. So let's look at this problem as an example of what we're talking about. So, large plate, drop, breaks into 3 pieces. Pieces fly apart parallel to the floor, so they don't bounce off the floor. They don't come back up. They just shoot horizontally. As the plate falls, its momentum has only a vertical component, and it's not moving left or right. When you drop it straight down, this makes sense. So after the collision, after it hits the ground, the pieces of the plate move horizontally. That momentum was non-existent before the collision. There was no horizontal momentum. So in this problem, the original momentum, we're going to assume 0. Here's another example. You could, if dropping a plate doesn't work for you, let's say someone put a small explosive inside this plate. Right? Same idea. All right? Plate bursts apart into 3 pieces. Before the collision, the momentum was 0. Total momentum was 0. This is like me, Shaq, and somebody else going to the rink. I know it's getting weird, but right? If you've watched earlier videos, this is like 3 people at the skating rink pushing off of each other. Still, all the forces are internal. Cool? But it's more than that, because not only is the initial momentum 0, that means the initial x momentum is 0, and the initial y momentum is 0. So we have to really do this problem, or look at this twice. Once in the x dimension, once in the y. Now I really don't know where to start, x or y, so we'll just pick one and go. I haven't done this problem yet. Kind of like doing it that way. So okay, don't know what I just did there, but we're gonna undo that. There we go. All right. So which one do you want to start with, x or y? Well, let's take a look. Let's take a look at our picture. Do we know the mass of any of these? Which one do we know the mass of? Find the mass of piece 1 and the mass of piece 2. All right, they don't give us. Oh yeah, they give us the mass of piece 3. My fault. You're right. I heard you say that. So I can find the momentum of this. The momentum of piece 3 is going to be what? Mass times velocity. So we're talking mass of 3 times velocity of 3. And by the way, this is final or initial? This is final, after they've broken apart. And that's a number that we can find. That's going to be 1.3 kilograms times 3.07 meters per second. And if you're following along at home, you have 1.3 times 3.07. I got 3.991. So the question is that the x component, the y component? What's the deal in terms of momentum 3 in terms of x and y? So it'd be a good time to note to yourself that since it is moving straight down, 3's final x component is 0 because it's not moving left or right. And the momentum we have here is really 3's final y component. And, well, keep in mind it is down. At some point we may need to assign a negative to that. We'll wait. All right. That's really the only information I have. So let's start in the x. Since we have that, let's start in the y dimension. Seems to me if they give us a bunch of information that's in the y, we should start with the y. So the initial y momentum has to equal the final y momentum. So we're just working in the y's here. So you have initially 0. Final, we have, well, let's take a look at it. We have 3's momentum in the y. It's all straight down. What about 1 and 2? Both of their y components are which way? Well, let's see. This one here is going, number 1 is going up and to the left. Number 2 is going up and to the right. So in terms of the y, both of them are up. So P, and this is final, so P1 y final is up, and so is P2 y final. Both of those are up. So this expression right here is going to be the combination of all 3. Now the question is, what should I do about that negative? I'm going to put it in as a negative eventually. So we're going to go with, we'll do this, minus P3y final. So the final momentum consists of in the y, consists of those 3, 2 up and 1 down. Now, one of them I know this one. So let's slide that over to the other side. So that means P3y final, add that to both sides, is equal to P1y final plus P2y final. Now this number I know, that's 3.991. This is M1 V1 final. Look at the angle they give you. What do you have to be careful of with that? Ask yourself that. That is not a reference angle. Now you have a choice. We could use the 25 and switch sine or cosine, or we could call this 65, recognize that that's a 65-degree angle. Your call. I'm going to go with the 65. I'm going to say that that's going to be times the sine of 65 plus M2 V2 final, its momentum, times the sine of, he forgets the angle already, 45 degrees. So these two are the components, the y components of those two vectors for 1 and 3. Sorry, 1 and 2. I know, if I remember, I know this, I know that obviously, I know those two. What I don't know is mass 1 and mass 2. So what do I need to do? Well, whenever you have two unknowns, start looking for another equation that has those same two unknowns. And in this case, I think the best bet is the dimension we haven't looked at yet. And that is, let's go to the x dimension. So let's do the same thing, but in the x dimension. Sorry, fine. Once again, it starts with 0. In the x dimension, mass 3 doesn't have an x component. Momentum 2, x final, is to the right, and momentum 1, x final, is to the left. The x component of momentum 1 after the separation. And these are the only two. And they're opposite each other. So let's say momentum of 2's x component after the collision minus momentum 1 x component after they separate. In other words, those two have to be the same. Now, the next step is the one that you're going to want to double check for yourself. Can you write down what's next, which would be the momentum of this, M1 V1x, just V1. We're not going to get to the x yet. We're going to use the cosine for that. So V1 final times the, let's make sure we get this right. 1 is up and to the left, so it's going to be cosine of 65 equals M2 V2 final cosine of 45. Now the momentum part is done because we know this, 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 and this. Everything else from here on out is just some algebra. I think probably the best way to go here is this. Let's replace, well, let's solve for M1. We'll call that M2 times V2 final times the cosine of 45 divided by V1 final and the cosine of 65. The reason I've done that is because I can take this garbage right here, since it's equal to M1, and replace M1 with it right here. And from that, the only thing I'll miss is M2. The most important thing here to notice is that the momenta in each dimension have to, in this case, equal 0 because that's what we started with. And we have to treat them separately. What's that?